Hello, I'm Makoto Sasaki from Nihon University. So today I will talk about trapping of drift wave turbulence interacted with zonal flows. Before introducing my motivation, I will show you briefly the structure formations in fusion plasma. So in fusion plasmas, there is very strong temperature and density gradients, which drives turbulence. And turbulence interacts with each other to generate the large scale flows or vortex. So this is a toroidally symmetric flow. This is called the zonal flow. The interaction between turbulence and large scale flows determines the space-temporal behavior of turbulence, and which determines the heat and particle losses. So I will show you the spatial-temporal dynamics of turbulence obtained in simulations. So in plasmas, sometimes the turbulence shows a ballistic propagation or spatially localization. So this figure shows the radial profile or a time evolution of radial profile of turbulence intensity. So the color shows the turbulence. We can see that there is a spatially localization of turbulence in addition to the ballistic propagation. So both are observed in this simulation. But with the different plasma conditions, you can get only the ballistic propagation or only the spatial localization. So the question arises that how is the selection rule of propagation or localization determined? So before considering the selection rule, I will show you the relation between turbulence and flow profiles. So the turbulence profile is a symmetry to the sign of flow curvature. So this is the simulation result. So this is a radial profile of the toroidal flow and turbulence driven heat flux. Yeah, so you can see that the heat flux is reduced where the flow curvature is negative, but in the flow positive curvature region, the heat flux is enhanced. So the heat flux is asymmetry to the sign of flow curvature. So this asymmetry has been observed in many simulations, including gyrokinetic and fluid simulations, and in experiments as well. So this profile cannot be explained by simple formula. So sometimes the heat flux is modeled like this. So the heat flux is modeled as a suppression that is introduced here. And here you can see the flow shear. And there's no curvature in this formula. So it's independent on the sign of flow curvature. So if this model is valid, the turbulence intensity should have twice the wave number of zonal flow because for this case, the turbulence is independent on the sign of flow curvature. Turbulence trapping is a strong candidate to explain that asymmetry. The turbulence trapping is introduced by wave kinetic theory, so I will briefly introduce wave kinetics. The wave kinetics is based on the scale separation assumption, assuming the turbulent wave packet as particles. So this wave packet of particles turbulence, and which is modeled as a quasi-particle. And we consider the interaction with the large scale. The distribution function of turbulence is given by a Wigner function, a Wigner transformation of the turbulent fields. So now I will consider the interaction between turbulence and zonal flows by wave kinetic models. In a wave kinetics, we consider the turbulence distribution functions as a function of a real space and wave number space. This consists of the phase space. And this distribution function is governed by these equations. So this equation is mathematically very similar to the Boltzmann equation, like this. So this is a velocity distribution functions. And for the wave kinetics, we consider the distribution function of the turbulence intensity. So for the velocity of the turbulence is given by a group velocity of the turbulence. So the group velocity is given by this equation. And the force acting on the turbulence is given by a spatial inhomogeneity of the Doppler shift due to zonal flows. So the zonal flow acting as a electrostatic potential in the Boltzmann equation. So this is the wave kinetics. And if you have inhomogeneous flow profiles, you will get the deformation of eddies. The deformation of eddy is written by this equation. So the turbulence trapping is a consequence of a nonlinear resonance of turbulence with zonal flows. In the Boltzmann system, particles are trapped in the potential. So it is very famous for the BGK vortex. So if at the resonance point, the turbulence is captured in the potential, and the distribution function becomes flattened, which forms a vortex in the phase space. This vortex is called BGK vortex in the Boltzmann. For the similar thing happens in the wave kinetic systems. In the wave kinetic systems, you will have a BGK vortex. It's like this. So this is a phase space diagram of the dispersion potential. So this is real space, and this is a radial wave number space. And if you plot the dispersion relation, you will have an island. This island corresponds to the BGK vortex. And as a consequence of the formation of the vortex, you will get the turbulence trapping and the zonal flow. So as a consequence of the trapping, the turbulence profile becomes asymmetry to the sign of flow curvature. So in this case, the negative curvature region, turbulence is localized, and at the positive curvature region, no turbulence is obtained. So this kind of asymmetry is obtained by the trapping theory. So the contents of this talk is as follows. First, I will show you the selection rule of propagation or localization of turbulence based on a wave kinetics. And second topic is to consider the turbulence asymmetry with zonal flow curvature based on fluid model. So first, I will show you the selection rule. So our model is like this. So we consider turbulence trapping in toroidal plasmas with the profile evolution. So we consider density gradient, which drives drift waves. And the drift waves drive zonal flows. And the zonal flow is written in the written like this, if you consider the toroidal geometry. So, and in the wave kinetics, you will have a shearing effect into zonal flow. So this couples with the Reynolds stress of the zonal flow. So the numerical simulation of this model is performed. First, I will show you the yeah.
Sorry, just because I didn't understand.
Yeah, okay.
How is the Reynolds stress calculated?
Okay, Reynolds stress is a function of the distribution function IK. Yeah, so the Reynolds stress is the integration of the IK with some coefficient. Okay. And so before showing the numerical result, I will show you the zonal flow characteristics in our model. So our model contains two branches of zonal flow. So one is the geo-frequency zonal flow, which is called the stationary zone. So because the stationary zonal flow is zero frequency, so no propagation, no phase propagation. And another branch is geodesic acoustic flow, which has a finite frequency. So because gamma has a finite frequency, it can propagate radially for the phase. So the phase speed is finite. And you will get a damping rate like this. So the parameter, the safety factor, controls the damping rate of zonal flow and gamas. So this is a plot of the damping rate. In a small safety factor case, the stationary zonal flow damping is very small, while the damping is large. But if you increase the safety factor, it can be opposite.
This damping.
Yeah.
Where
Data?
the plot that you're showing.
This one and this one? Okay. So the red curve is the damping rate of gamas. This term. And the yellow one is this term, the damping rate. Yeah, zonal. Okay, so we can control the damping rate of zonal flow and gamas by changing the safety factor. So we get a bifurcation between gamas and zonal flow dominant. So we perform a numerical simulation of a model by changing the safety factor shot by shot manner. And we plotted the energy of zonal flow, stationary zonal flow, and energy of gamas and energy of turbulence. And if we increase the safety factor, the energy of stationary zonal flow suddenly drops around here, and gamas becomes dominant. So this kind of bifurcation is obtained in our model. And if you see the turbulence behavior, and so this is a turbulence in the radial profile of time evolution of radial profile of intensity of turbulence. And the zonal flow dominant, the turbulence is localized in space. Yeah, numerical simulation of this model. Yeah, wave kinetic equation. Okay. Okay, turbulence intensity is defined by the integration of IK distribution. IK, okay, I will show you later. This one. So if you look at this regime, you will get this pattern. So this is a zonal flow, a stationary zonal flow dominant. So this is the phase space distribution function and a time snapshot. So this is X, real number, real space, and this is wave number space. And this color shows the intensity of turbulence. And if you integrate over the wave number, you will get the intensity of turbulence. Okay. So we can see that the turbulence is localized around here. And we plotted the zonal flow pattern. The blue one is the zonal flow. So we can get the turbulence. The turbulence is localized where the zonal flow curvature is negative. And at the positive curvature region, no turbulence is obtained. So the asymmetry of the sign of curvature is obtained, and turbulence is trapped where the negative curvature region. And because the turbulence is localized around here, the particle flux is enhanced only around here. So the density flattening occurs around here. So this is a density profile, radial profile of density. So the density is flattening where the turbulence is localized. And as a consequence, the staircase-like corrugation is obtained. Now, what is interesting is that the turbulence is strong, where the gradient is weaker. So because the profile is a consequence of the localization of turbulence.
And your growth rate doesn't have any correction from that, right?
No, we included. So
So
the-
the growth rate is corrected by the density.
Yeah, yes. So the growth rate is a function of density gradient, and we change it.
So very confident.
Yes. So maybe there is a competition between the growth rate or trapping. So maybe there is a competition, but I didn't consider deeply yet.
You have dynamics. So just showing the state here, how will the dynamics unfold? You cannot have drive where you will have really.
For this case, so there's no propagation in this case, and later I will show you the dynamical case. So if you look at the high safety factor case, the gamma is dominant, and the ballistic propagation of turbulence is obtained in this case. So this is movie shows the time evolution of the distribution function. And at the initial condition, inhomogeneous turbulence is introduced and without GAMs. And after the GAM is excited, the island is formed and the turbulence is captured in the island and propagate with each other. And as a consequence of this, the turbulence ballistically propagate. So this figure shows the time evolution of the GAM flow, and this is the intensity of turbulence. The intensity of turbulence is obtained from the wave number integration of the distribution function. So we can see clearly that the ballistic propagation of turbulence is obtained, and the propagation speed is the same as the phase speed of GAMs.
How do you excite the GAM?
GAM?
Yeah.
Okay. So we include the Reynolds stress term. So because there is a Reynolds stress here, the GAM is driven by turbulence. By turbulence. Yeah. Okay. So next I will show you the comparison of characteristic of turbulence propagation mechanism with other mechanisms. So we have a local linear propagation mechanism or turbulence spreading mechanism or avalanche. And so here we show you the turbulence trapping by gases. The propagation speed is very similar compared to others, but these two characteristics are different, and the trapping is very different from others. So if you consider the modulation amplitude of turbulence or the gradient, for the local linear case or turbulence spreading case, they are very similar. But in the trapping case, the modulation of turbulence is larger than the gradient modulation. Or the procedural change is different. For these cases, the gradient change fast, and then the turbulence is change. But for the trapping case, turbulence change fast, and then the gradient changes. So, experimentally, maybe these two characteristics should be examined. Okay, next I will move on the second topic. So we consider turbulence asymmetry with zonal flow curvature based on the fluid model. The turbulence trapping should be validated by a fluid model because the wave kinetic theory has while wave kinetic theory has a clear physical processes, but these have a large assumption like scale separation or ignoring the interaction between turbulence. So these should be considered and should be validated. So we consider Hasegawa-Katani model and 2D dynamic 2D direct simulation is performed. And okay, this is a density evolution equation, and this is for this evolution equation. And kappa is the density gradient, and alpha is adiabatic. Introduced by the Pat's talk today morning. So, and we will observe the behavior of turbulence when the adiabatic coefficient alpha is changed shot by shot. So, so we obtain the change of turbulence states with the adiabatic coefficient. So we evaluate the turbulence energy and energy of zonal flows. And at the small alpha case, the strong turbulence is obtained. And if we increase the adiabaticity, the turbulence becomes small and becomes almost constant. So the turbulence state changes with the adiabatic coefficient. Next, I will show you the simulation result, the spatial temporal evolution of turbulence. So I will show you the 2D evolution of density fluctuations and electrostatic potential fluctuations with the time evolution of zonal. So I will show you the black line, a zonal flow pattern by the black line. Okay, please.
Like kappa and dissipation.
Okay, and kappa is a density gradient, and alpha is a adiabaticity.
No, I mean what are the value?
A value.
So kappa.
Okay. Kappa is 1 in this case, and dissipation for alpha. Dissipation is very small, like 10 over -2 or -3. Yeah, yeah. So first, I will show you the alpha equal 10 case. So this is large adiabaticity case. So the turbulence behaves, and the zonal flow is formed like this, and we clearly observe that turbulence is localized, whereas negative flow curvature region. Okay? So this is very consistent with the trapping theory. But for the small alpha case, the situation changes. So this is zonal flow pattern. So turbulence is weak at the negative curvature region. But for the positive curvature case, so turbulence is strong. So I will show you the snapshot. Okay. So this is alpha equal 10 case, density and potential. The turbulence is localized at the negative curvature region. Negative curvature region, which is consistent with the trapping theory. But for the small alpha case, turbulence is strong, where the zonal flow curvature is positive, around here. Yeah.
Like how what the math going to build in
Sorry.
like what's the magnitude of the build in like calculate?
Okay. So
Because they generally
okay. So, yeah. So value is not written here. Sorry. So the zonal flow amplitude is order 1. order unity. So which is normalized by diamagnetic velocity. Okay, the order is very similar to the diamagnetic drift velocity. Yeah, both cases very similar. Same. So next I will show you the parameter regime of turbulence trapping. So we evaluate the strength of turbulence trapping by calculating a correlation between zonal flow and turbulence energy. So the correlation coefficient is defined like this: the zonal flow and turbulence intensity. And so the this correlation coefficient behaves like as a function of alpha. For the large alpha case, the turbulence correlation becomes around 1. So it corresponds to the turbulence trapping, which is consistent with wave kinetic assumption, because the wave kinetics theory is valid when the alpha is large, alpha is infinity. So, but for the small alpha, this correlation becomes negative. So which corresponds to that case that turbulence is localized, where the zonal positive curvature is at the positive curvature. So this is completely different from this case. So what is happening for the region of alpha in this small case? So especially at around here, alpha equal 1 case, so dynamical transition can be observed. So I will show you the dynamical behavior of turbulence pattern. Sometimes turbulence is trapped in the negative curvature region, but it changes to the state that the turbulence is localized at the positive curvature region. So this movie is too fast to follow, but I will show you again. So the turbulence sometimes trapped here or trapped here, or state changes, they're trapped here. So I will show you the snapshot. Yeah, the state transition can be observed. So sometimes the turbulence is localized at the negative curvature region. So these are the snapshots. And sometimes turbulence is strong at the positive curvature, like this. And these states survive for a much longer time compared to the typical time scale of turbulence. So sometimes the turbulence becomes this state, or it transits to the others. And why the turbulence can be localized at the positive curvature region? So that is the next question. So in order to answer this question, we will consider the eigenmode analysis of drift wave and the presence of zonal flow. By using the Hasegawa-Nakatani model, the density fluctuations or vorticity fluctuations are expanded in Y and T, and we consider the 1T eigenmode analysis with respect to X in the presence of zonal flow or zonal density pattern. So this is a radial profile zonal flow. So by linearizing the Hasegawa-Nakatani model, we obtain this type of dynamical equations, and the state vector is defined like this. And so we formulate this equation as a generalized eigenvalue problem. And we consider this eigenvalue problem. So the numerical method for the state vector K is defined like this. N1 and N2 should be are the values of density at the discrete point of X. So we have a very long eigenvectors. So the result is shown. For the first I will show you the eigenfrequencies. So these are the real part of the eigenfrequency. This is the imaginary part of the eigenfrequency. And we can see that from mode 1 to mode 4, these modes have a similar eigenfrequencies. So we plotted two groups, and several modes are degenerate. So I will show the eigenfunctions. So first, I will show you the eigenfunctions in which the turbulence is localized in a negative curvature region. So I will call these modes a trap mode in this study. So the first case is very periodic. So the turbulence is localized at a negative curvature region, and every curvature region, turbulence is localized. But if you look at the another mode, so sometimes this kind of mode appears. So the mode is localized here, no turbulence here, turbulence is localized here. This type of eigenfunctions can be obtained, and they are almost degenerate. But if there is a nonlinear interaction between them, this degeneracy could be resolved. If this mode is realized, the turbulence intensity is not necessarily periodic with the period of zonal flows. So, but this case is very consistent with simulations. So in the simulation case, turbulence is localized here, but no turbulence here. This kind of turbulence asymmetry is obtained from the eigenmode analysis. And if you look at the other eigenfunctions, we can get modes which are localized in a positive curvature. So we call this mode runaway modes. These eigenfunctions are very similar to the trapped mode. So there is a degeneracy with the eigenfunctions. And next question is, what determines runaway or trapped modes? In order to answer this question, we consider a diagram of trapped or runaway modes by using the propagation speed in the y direction. So we plotted the modes of the propagation speed, which is calculated from the real part of the eigenfrequency over ky. So this is the phase speed. And the blue one shows the trap mode, so which is localized in a negative curvature region. And the red one is a runaway, which is localized in a positive curvature region. So there is a very clear discrepancy between this and this. And the critical, there is a critical propagation speed. And this speed is completely same with the zonal flow velocity. So the clear relation between drift wave propagation speed and eigenstructures. And okay, 2 pages. So we consider effective potential by using the eigenfunction. So this is effective potential. So there is a curve, the frequency minus Doppler shift due to zonal flow. So if the frequency is larger than the Doppler shift due to zonal flow, there is no resonance. And the imaginary part of the effective potential become maximum at minimum of this one. So this mode, the mode is likely excited around maximum value of ky. So it corresponds to the negative curvature so the trapped mode. And for this case, there is a resonance in a resonance location. And the imaginary part of Q become positive here. So the mode is likely excited around the minimum value of Vy. So it corresponds to the runaway modes. And so this is consistent with the simulation. And okay. So this is the last one. The adiabaticity dependence is considered. So this is the ratio of number of eigenfunctions which are localized in negative or positive curvature. So this is the ratio of the negative curvature eigenfunctions. So around alpha equal 10, this becomes 1. So no runaway mode is obtained. So this tendency can be explained by behavioral frequency of drift wave. So drift wave frequency can be calculated as a function of alpha. In the low alpha case, the frequency is smaller, and this becomes large and saturated. And if you consider the Doppler shift due to zone of flow, in this case, the runaway modes can be excited, and around here, no runaway mode appears. So qualitatively, we can understand this diagram. And the summary is like this. So that's it. Thank you very much.